So, today we're going to dive into something, frankly, it's a pretty wild new idea from a recent paper. It's called the theory of integrated sticks. Let's get right into it.
And it all kicks off with a question that sounds, well, almost too simple.
How can a bunch of sticks, just simple sticks, be the key to building the future of our transportation and maybe even our future in space exploration?
Okay, I know what you're thinking. That sounds like a massive leap, right? But that's the whole idea behind this new framework. We're talking way, way beyond a simple raft here. All right, so let's get into the official definition. The theory of integrated sticks. It's a framework where you take sticks of all different weights, angles, and sizes. You interconnect them, and you form this single, solid structure that can float. But as you're about to see, its potential goes so much further than that.
And this is where it gets really, really interesting. The goal isn't just to build something that floats. The real aim is to create a strong, and get this, a dynamic framework. One that works on water, sure, but also on ice, or even in the zero-G of space.
So how in the world is that even possible? Well, the secret sauce is all in how these sticks are organized. It's all about a very specific hierarchy. Okay, so the whole structure is built in 6 nested levels. You can kind of think of it like a tree, with the trunk and then branches getting smaller and smaller. You start with these huge foundational main sticks. Then you go down a level to the macro sticks, then substicks, then microsticks, all the way down to nanosticks, and finally, the tiniest little components. The cool part is that each level supports the next one, creating this unbelievably intricate and strong system. The absolute best way to picture this is to think of a fractal. It's the same basic concept, sticks connected to other sticks, but it just repeats over and over again at smaller and smaller and smaller scales. And that's how you get this incredibly detailed, fully integrated structure.
But here's the thing. This amazing structure, it's not static. And this is where the theory gets really, really innovative. It's designed to be dynamic, almost alive.
So the paper itself uses these specific symbols to map out how all the sticks connect. But honestly, the idea behind them is super straightforward. You've got symbols for vertical connections, top to bottom, and horizontal ones, left to right. And then there's one for a central or neutral connection point. This basically becomes the blueprint, the language for designing the whole thing.
Okay, now this next part, this is what really just blew my mind. The paper says, and I'm quoting here, that all these integrated sticks can experience different changes such as expansion or contraction according to environmental changes.
So what does that mean? It means the structure isn't rigid. It's designed to be nonlinear, to be adaptable. Instead of just shattering under pressure like a stiff board, it can actually flex and absorb that force. This makes it way more resilient, way stronger.
And listen, this isn't just some theory stuck on paper. It's not just a mathematical model. They've actually put this to the test using 3D printed prototypes.
For instance, here you can see one of the prototypes being tested out on a liquid surface. And just like the theory predicted, it totally works. It floats, it holds its structure. It's amazing.
And then, to show just how versatile this thing is, here's another prototype being tested on a solid surface. This is all about checking its stability, its structural integrity. The whole point is to prove that this design can work in pretty much any environment you throw at it.
Okay, so let's recap. We have this dynamic, adaptable, multi-level structure, and it's already been proven in early tests. So what can we do with it? What are the real-world applications? Well, this is where we go from oceans to orbit.
And the potential uses they're proposing are, wow, they're incredibly ambitious. We're talking about advanced ships that can adapt to rough seas in real time, or new aerospace systems that can literally self-assemble once they're in orbit. Imagine adaptable structures you could build anywhere, from right here on Earth to a colony in deep space.
So, the crucial point, the main takeaway here is this. We're looking at a way to create a single, incredibly strong and resilient structure from literally millions of tiny, interconnected, adaptive parts. This is a whole new way of thinking about how we build, well, anything.
And that leaves us with one final, pretty mind-bending thought. Could a principle that was inspired by something as simple as a raft, could that one day be used to build a floating base on an icy moon? Or a habitat that builds itself in deep space? According to this theory, that future might not be so far-fetched after all.